Good morning and good afternoon, everybody. It is great to see how many of you have joined us here today, and welcome to this webinar, hosted today by Bandweaver. The speaker today is Richard Kluth, Managing Director at Bandweaver Technologies. Richard has been involved in distributed fiber optic sensing for 27 years. Richard started with a DTS Pioneer sensor and installed the first ever fiber optic in an oil well in California in 1995. He has gone on to hold both technical commercial positions and has been senior management positions for the last 15 years. Companies he has worked for include Sensor, Schlumberger, SenseNet, Action, and the Bandweaver Group. We encourage you to ask plenty of questions at any point during the webinar. Please type your questions into the Q&A box you'll find at the bottom of the screen. At the end of the presentation, we will present your questions and answer as many as possible. It is an absolute pleasure to have Richard with us today, and I would like to warmly welcome Richard now to take control and begin the session.
Well, thank you very much, Martin. Good morning, good afternoon, everyone, and thank you very much for taking the time to participate in our webinar. As Martin said, my name is Richard Kluth. I'm the Managing Director with Bandweaver Technology, and the title of my presentation is Mitigating Fire Risk in Tunnels, a System Approach to Underground Safety. So the objectives of this webinar are to introduce the main technology behind what we offer, which is fiber optic linear heat detection technology, and really show you, how do we use that to mitigate fire risks in tunnels. We'll demonstrate the benefits of these fiber optic sensors, and the main key points are that you get coverage at all points along your assets, and that it's a robust and reliable technology with a very low cost of ownership. We'll show the enhanced performance of these systems, some of the key features being rapid detection, a low level of false alarms, and that you get the precise temperature information, which means you can use it for much more than just fire detection. And finally, to highlight Bandweaver experience, and our fire laser linear heat detection system is the highest performing system available, and really to go through some of the examples of our extensive experience within the fiber optic linear heat detection applications. So the order I'll go through this, I'll introduce the technology. We'll talk through some of the practicalities of how you install it, how it all fits together, talk of the advantages of this fiber optic linear heat detection systems over some of the other systems available out there, and highlight that with some real life installation examples. And finally, I'll just give you a few details about Bandweaver, just to give you a bit of background as to who we are. So if we look at the overview of fire safety in rail tunnels, railways, they're an extremely environmentally friendly, extremely efficient way of moving both people and freight, and offer a number of key benefits, but they also come with their own risks and dangers, and fires represents one of those largest risks, particularly in a tunnel environment. If we look historically, there have been a number of high-profile catastrophic fires where, unfortunately, there's been loss of life. If we look at the examples of Baku and Karpun, if we look at the Eurotunnel, possibly the most high-profile tunnel in the world, there has not been loss of life. There's been 4 fires throughout its existence, and if we take the 2008 fire as an example, that cost an estimated £240 million in damages and lost revenue. So still, even without life loss, it can be a very expensive business. And the statistics, show unfortunately these occur surprisingly often. And if you take a 10-kilometre section of rail tunnel, typically you would expect a fire in a 15-year period. And if we look at the pie chart on the bottom right-hand corner that shows this cause of metro fires, you can see they're quite diverse, and so it can be very difficult to mitigate and completely prevent all these causes. If fire does break out, it can lead to dramatic consequences. The confined nature of a tunnel means that escape or evacuation is difficult, and toxic fumes and heat can build up very rapidly. Finally, when it comes to operational procedures, how do you mitigate, how do you detect? You can't always intervene, you can't always extinguish at all points in the tunnel, so it's very difficult. And there's different operational requirements as well. So if we take the example of drive on, do you drive on, or do you not drive on? Prior to the 1996 fire in the Eurotunnel did drive on. Afterwards, they decided to stop and evacuate. So in order to form such policies and strategies, operators need to have the best information possible, and linear heat detection forms a key part of that strategy. So this diagram, highlights the build-up of a fire in a tunnel environment, and typically starting on the bottom left, that they start quite small. If you can catch it early on, it can be quite easy to extinguish the fire. But in latter stages, once the fire really takes hold, temperatures can be in excess of 1000 degrees C. And in this case, there's little you can do to control the fire, and damage can be extremely extensive to infrastructure. It's therefore critical to detect the fire as early as possible. Before I go into the specific details of the fibre optic technology, explain how it works and what the advantages are, just wanted to give a little bit of history. To many people I speak to, hopefully some of you on this webinar today, it's a new technology, and it seems very exciting and very novel. But the reality is it's been around for a long time. It's been used in road and rail tunnels since 1986, so 35 years. And more than 5,000 systems have been installed in tunnels worldwide. So it's a mature technology from that perspective. And it started in road and rail tunnels. It lends itself to long lengths. But since then, it's diversified into many other applications. It's a very versatile technology. And so as well as rail tunnels have road and cables, buried power cables, oil chemical tanks, conveyor belts, and a number of industrial facilities. And what we'll see within this presentation actually was that within rail networks, as well as tunnels, operators are also increasingly using this in other facilities across the network. So why use this fibre optic technology? What are the benefits? Well, broadly, we can divide them into two sets of benefits. The physical and practical benefits, and the benefits you get from the improved information. So starting with the physical benefits, it's a very simple technology to install. So you have reduced infrastructure costs compared with alternative technologies. It's very robust. It's resistant to electromagnetic interference, intrinsically safe, corrosion-free, no moving parts or joints. So it has a very low maintenance, long lifetime. And it's resilient to cable cut and sabotage. So you have uninterrupted detection, even if the cable is cut or damaged. Moving on to the information benefits, you get very good location accuracy. The system can identify events to within half a meter. You have very early detection with this precise location, and smart alarms, it can detect quicker than with conventional sensors. And based on that, you get improved decision making, which allows the user to make more informed decisions and lower their overall risk profile. So what is the technology behind this fibre optic linear heat detection? It's known as distributed temperature sensing technology, or DTS technology. And really the key to this technology is the system uses standard telecoms grade optical fibre. So no specific specialist sensing points are required. This is because it uses technology called optical time domain reflectometry, which is a bit of a mouthful, so I'll call it OTDR, but it's very similar to radar time of flight principle. And the next slide, I'll go into a bit more details. But the key takeaway is the fibre is the sensor. There are no specific points, and you get complete coverage. So if we look at the typical setup, stripped down to its basics, you have the linear heat detection controller here, the box, and a cable that plugs into the box. The system sends a light pulse into the fibre. The laser pulse interacts with the fibre, and some light is reflected back to the controller. The time it takes for the reflected light to return gives the precise location, which is the very similar principle to radar. And by analysing the power and frequency of the reflected pulse, the controller is able to determine the precise temperature information at all points along the fibre. So depending on the sampling range of frequency of the system, how it's set up, you can get measurements from every half metre to a metre. Typically 1 metre is the standard. If you then install that cable within a tunnel environment, you get complete coverage wherever you are in the tunnel. So there's the advantage is there's no gaps, monitoring. And secondly, it makes planning and installation of the cable very simple. You don't have to worry where the sensing points are going. They're everywhere. And I'll just highlight the distributed nature here with an example comparison versus a conventional point sensor system. So if we imagine we have a fire at this point in the tunnel, the cable would sense the heat directly above it, and so you'd have a very fast reaction time for that thing. Again here, another small fire, you would have it directly above, and wherever you are, you get the picture. Wherever it moves, you would get it straight away. If we look at a multi-point line type system, and this is a system with multiple sensors, I believe sort of up to 250, but when you put this in a tunnel environment, they can be more than 10 meters apart at times. And when you have a fire, there's a bit of a lottery as to whether it's below a sensor or not. So in this case, it isn't. In this case, it isn't. And when it isn't, it won't detect the fire till much later, till it really spreads and the heat spreads. In some cases, you will get it, but there's no guarantee that you'll get it every time. So the distributed F has a number of benefits from that perspective. So now we've sort of introduced the main components. Let's look at more detail of each of the components and the practicalities of, how do they work and how would you install it in a tunnel environment. So we'll start with the controller. The controller is the heart to the system. This is the fire laser by Bandweaver linear heat detection controller. This can go up to 10 kilometers in range, 4 channels per unit, so up to 40 kilometers or 40,000 measurement points if you have it set at the 1 meter level. The controller is fairly compact, completely self-sufficient. You can configure and program all through this touchscreen LCD here. You have the channel indicator, so you can see which of the fiber optic channels is in operation at the time. Standard indicator lights, so if you have an alarm, a system fault, laser operation, power operation, and a lockable access panel with additional functionality such as a very fast alarm reset and mute, but only accessible to those with the appropriate levels of authority. Looking at the back panel, starting at the right, we can see the fiber optic connectors. This is where the sensing cables plug into. These are simple plug-in connectors known as E2000 connectors. We move to here, we have the Ethernet and serial ports. This is for the Modbus connectivity. And then we have the relay connection ports. As standard, it comes with 50, which interfaces with the fire control panel. And then the power supply, which is 24 volts DC, which is usually supplied from the fire control panel. Moving on to the sensing cable. As we said, the sensing cable is based on standard telecoms fiber. It means it's totally passive, no moving parts, so no maintenance is required. It's not susceptible to corrosion. So this cable's lifetime is often in excess of 30 years. Other benefits of the fiber optic cable is it's immune to electromagnetic interference, no in-field power or communications requirements, which reduces any additional cost and increases the reliability. It's very lightweight and flexible. Typical, these are in the region of a 3 to 5 millimeter diameter. So it means they're very easy to install while also offering sufficient protection for the rigors of installation and for the cable lifetime. So if we look at some of the examples on the right here, we have the Firefaber AT, which is a metal-based cable, and a TT, which is a non-metal-based cable. The cables have a similar sort of principle. You have the fiber at the core here, a metal tube which provides, or a thermoplastic tube which provides crush resistance, layers for tensile strength, which is steel braiding, Kevlar, and then an outer layer for protection. And the reasons why you'd use metal versus non-metal, in some environments, if electrical conductivity along the cable is a concern, some customers request a non-metal cable. The cable needs to be attached somehow. Here's an example of some cable fixtures typically used in the tunnel applications. These are usually attached to the ceiling and the wall. And depending on the tunnel, the different partners, the different customers, different styles of fixtures are used, but they have a commonality in which the cable is usually attached to the fixture at an offset from the wall or ceiling to maximize the sensitivity and typically they're installed intervals of 1 to 1.5 meters. And where do you put the cable? Well, in most linear heat detection applications, it's normally at the highest point of the room or the facility, because that's where the heat gathers and is the hottest. For railed applications, this is not always the case, as there's potentially overhead cables in the way, and also fires quite often initiate around the wheelbase. So the preference tends to be on the wall, but this is always decided in conjunction with the client. Normally it's one cable can cover a dual tunnel of till trains, but again, it depends on the cable position, size of tunnel, and client preferences. So that would always be one of the discussions that's had early on. So if we look at some cables in situ, and we'll go through some more case studies later, but this is an example of a ceiling mounted cable on an extended bracket here, a ceiling mounted cable here. And on the right, we have a picture of a team commissioning the equipment in situ. Here they're using a heat source on a pole to simulate a fire event, which, as I said, in this case is used in commissioning, but is also used on the regular checks that are carried out throughout the lifetime of the project. In terms of how does the system integrate with the fire control system, there's essentially two methods for this. So the simplest is electrical relays to the fire control panel. So each alarm has an electrical relay which would correspond to the zones in the fire control panel, which would trigger in the event of an alarm. And Modbus over TCP/IP typically, which is either to the building management system, ventilation control, SCADA system, and that carries more information. There you can get the absolute temperature, the absolute alarm value, the distance. So as we see when we go later, you can get much more benefits from that additional information. So we've talked about tunnels, but what we're increasingly seeing is that operators are tending to use this in other parts of the network as they understand the flexibility and the benefits of this. So in addition to tunnels, they're used in and around escalators, station and platform concourses, and these are typical installed in the ceiling, typically within a ceiling void is most of the applications, and also the facility buildings around the network, and again typically installed in the ceiling voids. And finally, electrical assets, so quite a wide range around the network, and we'll see that in the later case studies, some of those examples. So moving to the advantages of these systems, I'll start with talking about redundancy. This system has some unique redundancy configurations that it's worth spending some time on. We'll talk a lot of smart alarms and smart zones, which is really the heart of this technology, describe what they are and what the comparison, how do they compare with other linear heat detection systems, and give some examples, run-throughs of performance in the tunnel to really illustrate how they work. And finally, talk about the integration and the benefits you get with the added data. So starting with redundancy, with regards to reliability and redundancy, these are critical to the end user. And so typically we find in rail tunnels some level of redundancy is required. And that for this technology can either be at the controller level or at the cable level. So two things. At controller level, you have continuous operation in the event of a controller failure, and cable continuous operation in the event of cable cut or damage. This first example I'll work through shows a single tunnel and two controllers. But what we'll see is that as we go through to multi-tunnel configurations, you get economies of scale with more tunnels. That means you don't need two controllers per tunnel to have redundancy. So going back to this example, what we have here in the example is a single tunnel and a controller on the either end of the tunnel. We have a single cable running in the tunnel, but this cable has two fiber optic cores at the center. So the red one is attached to system 1 and the green core is attached to system 2. So when both systems are operating, you can see the red pulse travels to the end of the fiber, reflected light goes back to number 1. Similarly, number 2 travels to the end of the fiber, comes back. You have full coverage on the tunnel from both controllers. If controller 2 was taken out of service, you see controller 1 would still send the light to the end of the tunnel. You have absolutely full coverage while the system could be under maintenance or repaired. Similarly, if controller 1 is taken out of the loop, you have full redundancy. So in this scenario, it's not that difficult from typical system redundancy, but you notice in this scenario, we've put them at either end of the tunnel for this specific configuration. And the reason is that in this configuration, you can get cable cut redundancy. So in the event you have a cut in the middle of the cable here, you can see that each system can measure up to the cable. The light can't pass past it because there's a break there, but the reflected light comes back. And so you still have full coverage with the cable cut. So with this particular configuration, you have, as we said, full controller and cable cut redundancy. If we move to an example with 2 tunnels, still with the 2 controllers, you have the same controller and cut redundancy. So these 2 controllers still monitoring this top cable here, but now they've got a second tunnel, second cable with a second channel on each controller. So as you increase the number of channels, you can increase the redundancy operations. So in this case, we have two controllers, 2 tunnels, so 1-to-1. As I said, in some cases, customers only want the cable cut redundancy, not the controller. So if we move to a loop configuration, for example here, 1 controller can provide the cable cut redundancy for 2 tunnels. And a cut anywhere would mean you could measure from both sides. So there's real sort of versatility and flexibility. And as we said, economies of scale, as you build up across the network with these systems, the ratios get even better. So this example shows 4 controllers and 6 channels. Apologies, there's a lot of wiring in here that is quite difficult to follow through, but I can run through it when anyone afterwards if they want. And you can see in each scenario, if you have a cut or a controller loss, you would have full coverage. So it really goes to show, as you build this up through the network, the economy scales are really good for this technology. So moving into smart alarms and smarter zones, which I said is really the heart of this technology. The key benefits are the early detection, detects faster than conventional alarms, reduced false alarms. You can customize each specific environment zone to the environmental conditions to really hone in on it, to reduce any potential alarms from that. And you get improved information, the temperature data, precise location, the accurate temperature means you can use this for ventilation signal control, what we'll look at. So what do we mean by smart alarms? Well, broadly speaking, there's 3 types of smart alarms. The absolute value, rate of rise, and deviation or differential alarm. So absolute value is similar to conventional sort of point sensor alarms in that if you exceed a value, the alarm goes if you go over a certain temperature. However, with this is fully software configurable, so you can set the level at whatever you want, and you can set multiple levels, so you can have pre-alarms. So it gives you a lot more flexibility. If we take the example of a copper-based linear heat detection system, the alarming temperature is defined by the physical properties, i.e. when the polymer melts and softens. So once you've selected, there's no changing. If we move to the rate of rise, this corresponds to how quickly the temperature rises within a defined time period, which is typically a minute. And one of the advantages, this can detect much earlier than the absolute temperature alarm. Typically for a tunnel, rate of rise would be in something around 9-10 degrees C per minute. The absolute temperature may be 58 degrees. If we think the ambient temperature of a tunnel is anything from sort of 10 to 30 degrees on average, you can detect much earlier than before the temperature has to reach 58 degrees. It's a very efficient way of alarming and buying valuable time. And similarly, the temperature deviation alarm, this triggers when there's a temperature peak within a zone that differentiates it from the average value. And again, sort of 9 or 10 degrees C is a typical value for a tunnel. And this would trigger much earlier than the absolute temperature alarm. But in some cases where you have a slow burning fire, the rate of rise may not trigger, and so the temperature deviation or differential alarm is a good tool to have in the armory. If we move on to smart zones, I'll describe what we mean by these. So these are software configurable zones. You can define up to 1,000, and you have complete flexibility in terms of overlapping and how you define them. So if we look through this is a screenshot of the software, it just gives you an idea of how these alarms are configured. So this is the details for a zone. You would give the zone a name, something intuitive, or the name that corresponds to on the fire panel, which optical channel, which relay is activated, where it starts, where it stops, and then all the different temperature smart alarms that you put in there. And you can have multiple alarms for a zone, so it's very powerful. So to sort of highlight how they work, I thought we'd go through a tunnel, examples of fire in a tunnel, comparing different linear heat detection systems and how they compare. So we've got 3 tunnels here. The top one, the fiber optic linear heat detection system. The middle one, a conventional copper-based linear heat detection system. And the bottom one, which is a multi-point line type, which has electronic-based but many individual sensing points throughout the tunnel. So first point to note, they're all installed, broadly speaking, in a similar way. They're attached at the roof or the wall and the tunnel. For this example, the ceiling. The first 2, the fiber optic and the conventional, have continuous coverage. You have coverage everywhere in the tunnel. The multi-point only where the sensors are. And as we said earlier, they can be they can be more than 10 meters apart. The fiber optic linear heat detector can measure temperature, so you have accurate temperature at all points. The conventional cannot, the multi-point does. So measuring the temperature enables you to have the smart alarm functionality. And the smart alarm functionality, as we said, is the configurable absolute alarm, in this case set to 58 degrees C. The conventional one, for this example, we're using 58 degrees C, but it's not variable. It would be selected by the material selection. The rate of rise of the multi-point and the fiber optic is 9 degrees C. The copper-based LHD doesn't have rate of rise, and the deviation alarm of the fiber optic and the multi-point 9 degrees, again no rate of rise with the conventional. So if we look at a fire in a low wind speed tunnel, we look at a 10-meter section of tunnel. It behaves more or less as you would expect. You have the fire, the heat is hottest directly above the fire, it's hottest at the ceiling level, and it reduces the further away from the fire you go. If we look at each of these points, 1, 2, 3, 4, and how the temperature develops over time, you can see it steadily rising, a little bit less as you get further away from the fire. You can see this red line is the absolute temperature alarm. And so this is when it hits, is when it's triggered. So you can see how many minutes it triggers in. But you can see in all cases, it triggers the absolute alarm a bit slower the further away you are from it. And if we look at this matrix here, the absolute rate deviation at each of these zones, we can see what the timing is at each one. I won't go into all the details at this point, but broadly speaking, you see pretty much everything triggers except for in zone 4, it's not quite fast enough to do the rate of rise, but otherwise you get full alarming at all zones. So what that means is the fiber optic linear heat detection, it triggers in all zones. The conventional linear heat detection triggers in all zones. That's predominantly because they've got full coverage. The multi-point triggers, but it triggers only in the zone where it has the sensor within the time frame. And the time frame is that the fiber optic linear heat detection triggers in 1 to 2 minutes. The other system's 3 to 5 minutes. So this buys you 3 minutes extra time, which is valuable extra time to prevent damage and save lives. If we stay on this theme, stay in the tunnel, but go to higher wind speeds, the system gets more complex. What we see is the temperature is not necessarily hottest above the fire. It's not necessarily hottest at the ceiling, as that it's blown down the tunnel. The heat can burn very fiercely, but the hottest temperatures are lower down, and it gets hotter the further away it goes. So again, if we look at the temperature evolving over time, what we can see, one clear point, is that at ceiling level, it doesn't get close to where the absolute value temperature is. So the absolute alarm would not trigger in this scenario. And which alarms do trigger? It's a mixed picture. Deviation in some zones, rate of rise in some zones, but not in others. So which systems would trigger? So the fiber optic triggers in 3 out of the 4 zones. The other systems would not trigger within that time frame. So again, it triggers within 1 to 2 minutes. The only one to do, but still in the same time frame. So if we revisit this slide again and re-emphasize the importance of early detection, which we've shown the fiber optic system can, I think it's then important to look at multi-channel examples, because the scenario changes when you move to a multi-channel fiber optic linear and heat detection system. So if we look at this 4-channel system here, we have the controller at the center, we have fiber optics moving into different parts of the tunnel. So all 4 cables are covering different parts of the tunnel. And you can see the fiber, this glowing light shows the laser light within the fiber optic. And so what you can see is only one cable is active at any one point. So the other 3 are not being monitored while that one's active. So you want to make sure you cycle through as quickly as possible, so you're getting, you're not having big gaps in any coverage. But then also it's important we talked about the rate of rise. With the rate of rise, you have to have 2 cycles to get through. You have to see the change in temperature. So that again changes the dynamics of how fast the measurement is. So if we look at the maths behind that, so rate of rise takes 2 measurements per channel. So for a 4-channel system, that means 8 measurement cycles to get a single rate of rise measurement across the whole tunnel. If we say we take 5 seconds per measurement, which is a typical time for the fire laser, that means it takes 40 seconds to get rate of rise measurement across all the tunnels, which, in the context of a tunnel is a reasonable time frame, but you certainly wouldn't want to make much longer than that. And the approvals dictate that you have to do it in about that time frame. And so with the fire laser, we have the fastest system available. It's 5 seconds response time for distances up to 10 kilometers. That means a maximum of 40 seconds between rate of rise of measurements. And this is up to 6 times faster than competing systems, which can take 30 seconds per channel at the longer ranges. So this means the fire laser is the only system that can operate at the longer range with 4 channels, which means you have more measurements, greater coverage per controller, and makes it a much more cost-effective solution. So the final advantage we'll be talking about will be the smart zones, and how do you use that temperature data? So in addition to fire detection, information can be used to ventilation control, to adjust the fan speed, when to turn them on or off, coordination of video CCTV feeds, for example, used in conjunction with evacuation or initial incident investigation, and environmental management if the tunnel has climate control issues. And the key to the smart zones we're saying is that you do get the accurate temperature data and the precise location. And then with the multiple different zones types, you can then configure them according to functional requirements. And this can be different lengths, different alarms, and they're completely independent and overlap. So if we look at the schematic of a example of some different tunnels within a system, what we see is on this axis on the bottom is the length along the tunnel, and then these are each of the different systems. So linear heat detection, ventilation control, signal control, lighting, and fire suppression. So the linear heat detection is divided into 10 zones, and that corresponds with the 10 zones designated in the fire control panel. The ventilation control would be decided by how many fans there are in the tunnel. In this case, there's 3 zones. Signals, how many signals? In this case, saying just 1 signal per section, so it's a binary decision. And the lighting, 4 zones, fire suppression, many more than in the zone. And so what it really allows you to do is set the alarms to control and get better information for each of these zones. For example, for the suppression, to really focus resources and potentially limit water damage in the event you do need to activate the systems. So now we sort of understand the technology a bit, seen the principles. Let's look at some real life installations, and we'll look at some tunnel installations. We'll look at Metro Dalian Metro in China, Madrid Airport rail tunnels in Spain, looking at the station platform monitoring and a mass rail transit system in Singapore, and facility buildings of the Land Transport Authority in Singapore. So starting with the system in Dalian Metro in China. In this case, the system was used for tunnel monitoring. There was 1 linear heat detection system per station. And if we look at this architecture on the right, you can see how it's set up. It was a 4-channel system with 2 channels going either side, monitoring one of the 2 tunnels. It monitored to the halfway point between the next station, at which point the neighboring station would take over the other section of the tunnel. And this was the architecture that the customer wanted, that every station was completely independent, self-sufficient, integrated. So there was 50 stations installed, so 50 LHD systems. Integration was via relays and Modbus, and there's also some bespoke custom software I'll show you in one of the slides. The cable was installed at a ceiling just offset to the left. You can see it there in the photo and the schematic. And it was a rack mounted system. Here we can see within the control room. So this is the fire laser linear heat detection system here. It's connected to the fire control panel in the rack next to it. Also, the integrated supervisory control system, the ISCS, is in the same room via Modbus. And then you can see just the GUI, graphical user interface I was talking about here, where this had some additional functionality the customer requested. I wouldn't say this is typical for a tunnel installation. They wanted this for this particular customer. Because there's 50 stations, they got a lot of economies of scale, be able to roll out a similar format. But typically, we only get this for more sort of complex installations. Moving on to Madrid Airport, the tunnel monitoring there. So we installed in 3 systems, 3 separate tunnels, each 2 kilometers. In this case, the systems were installed with the cut resilient loop configuration. So in the event of a system cut, you would have full functionality. This system was installed in 2014. So the mean time between failure for this project is more than 21 years and increasing. And it gives an illustration of the reliability of this system. Moving on to station monitoring. So for the mass rail transport in Singapore, they monitored platforms and concourses using this technology. They installed the system in the suspended ceiling, in the ceiling void. And just worth emphasizing, they also monitored the tunnels, but once they understood the benefits and versatility, they used it quite extensively through the nation. And the reason they did this over using conventional point sensors is they found that there's no power supplies or land comms cable needed within the ceiling void. The dust, typically point sensors or beam detectors, dust can cause failure and false alarms, so it's not susceptible to that. And it's also easier to test and maintain. You don't need to get into the ceiling void to repair the cables. If we look at the cable route, we can see the cable runs backwards and forwards across the station and concourse. The spacing between those is based on sort of standard spacing standards that will be applicable to the point sensors. And here we see some photos of it in situ. So you can see it running backwards and forwards within the ceiling void. Here you can see a close-up of a clip. As you see, it's quite simple to attach to the ceiling. This picture on the bottom right highlights the difficulties of working within an enclosed space in the ceiling void. So keeping it as simple as possible is critical. Here we see the wall-mounted system next to the control panel. The other one was a rack-mounted. This is a wall-mounted. So again, shows you the different architectures of installation. The Land Transport Authority in Singapore, they installed the system for their linear heat detection for the facilities building, integrated it with the water mist system. And again, it's at ceiling level. And the reasons implementation over point sensors is very similar to the station and concourse. Higher reliability, simpler installation, lower levels of false alarms caused by dust and particles, which is an issue in these spaces. So here we can see, along the left one, you can see the cable at the ceiling height, and you can see it running in parallel with the water mist system here. And you can see it throughout the facility, different areas, different heights. Again, with the different smart zones, you can really divide this up and fine-tune the alarms to how you want to for each section. Really powerful and versatile technology. So finally, a few words on Bandweaver, the company. So Bandweaver has been in operation for nearly 20 years now. We have vast experience. We've installed more than 3,500 systems, more than 30,000 kilometers of sensing cable. There's more than 300 of us worldwide. Some of the key technologies we have are distributed temperature sensing, which we've addressed here, how it's used within linear heat detection. Distributed acoustic sensing, I haven't touched on it in this presentation. We probably need a whole other presentation for this. Hopefully there'll be an opportunity in the future to go through that. In terms of global presence, we have facilities across 5 countries, so USA, Canada, UK, UAE and China. I'm based in our UK office, our London office, and manage the UK-based entity. Regarding the international standards, these are clearly critical both for fire detection and specifically for the rail industry. So below are some of the standards we adhere to, some of the bodies we work with in terms of implementing and getting certified. Reliability is also top priority Bandweaver and something we work very hard on. The fire laser MTBF is greater than 29 years and is always something we're monitoring and striving to improve on. We work with some of the global leaders within fire detection, security and the rail industry. Here's a sample of some of the customers and companies we work with on a global basis. And we're a trusted supplier. We have extensive repeat business, and we're keen to keep expanding this client base, and we have the capacity to do so. And so, conclusion, I'd just like to sum up in a few words what we've looked at. So, fibre optic linear heat detection, one of the key benefits is it provides complete coverage at all points along the asset. There's no gaps, no areas left unmonitored. It's an extremely reliable and robust technology with no moving parts, immune to electromagnetic interference, not susceptible to corrosion. The cable's lasting longer than 30 years. It means you get a very low cost of ownership over the lifetime of this project. In terms of performance versus conventional systems, the fibre optic linear heat detection system is excellent with faster detection, lower levels of false alarms. And in addition, you get the precise temperature information. So you can expand the application to more than just fire alarms. You can get value-added information. With the fire laser, you have the quickest and most responsive unit available in the market. And Bandweaver has extensive experience for nearly 20 years and a trusted partner to many companies. So on that note, I would like to thank you all that time and open up for questions.
Richard, thanks for that. That was absolutely superb. I've got some questions here for you. I'm going to dive straight in. The first question is from Fernando. And the question is it 10 kilometers for each side or 10 kilometers in total?
It's 10 kilometers for each optical channel. So, so you can do up to 40 kilometers from one channel. So you could go up to 10 kilometers away from things. And so quite often what the operators do is wind the cable. So they might do a few kilometers in the tunnel, and they might wind some in the platform, and then wind some more. And you can splice it very easily at any points as well. So how it's configured in different networks is very different depending on the scenarios. But the headline figure is 10 kilometers per channel. So you can choose the number of channels up to 4 for linear heat detection. So up to 40 kilometers. That answers.
Thank you very much. Another question for you, Richard, from Quinton. Dear Richard, thank you for the presentation. Do you design yourselves the optical cable, or do you have another supplier?
We do design the cable ourselves. When we work with, it's sort of both. We work with manufacturers with that, but yeah, we have the expertise in-house to do that. If we move into some more specialist applications, we may work with kind of a three-way thing with the customer, with a specialist supplier ourselves. So examples of that can be for tank monitoring, where chemical resistance of the fibers is particularly important. Sometimes customers want to go to higher levels of temperature, furnace monitoring kind of environments with that. So there it becomes more complicated. But for standard rail applications, yeah, it's our cable, our design.
Thank you very much. Another question here from Farouk. You mentioned system works even if there is a cut in the cable. Could you please explain this? If the cable is cut damaged, how does the reflected light travel back to the controller?
Right. Let me go back to. I'll go back to the. Yeah, that's a very good question, and this is the this is the bit that's sometimes really difficult to see until you see the technology in action. But I'll go back to this one. And the key is that it's the fiber is the sensor. So you've got the pulse as it goes into the fiber, as it's traveling through there. And obviously this is the speed of light, so it's slowed down infinitesimally. You're getting reflections back as it goes out due to the natural interaction with the glass. So the glass has vibrations. As you get temperature in that, it flecks the vibrations, and so the light that's reflected back is affected by that. And it's a tiny amount. That's why these systems are so clever, because it's really taking the noise out of the signal to noise ratio, getting rid of that and getting back these tiny amounts back. But it's you're measuring this background. So if you say had a break, at this point here, your pulse would still be going to there. So you're not waiting for the pulse to get to the end to measure. It's as it's traveling, the light flows. So the electronics in the box are sampling super quickly, hundreds of kilohertz, in order to get that. So as soon as the pulse is on there, it's faster than we can comprehend as humans. But with the advent of high-speed electronics and processing over the last 20 years, this has become really accessible and affordable technology. I hope that answers the question, but the reality is sometimes you just need to see it in action to really get the thing, and then to see the distributed temperature profile along the whole length is quite amazing, because it's not like conventional ones where you have the individual point and you get it at that point. It's everywhere, and you are getting that light reflected back at all points.
Many thanks for that. Another question for you from Fabrizio. What is the temperature accuracy of the measurement time of 5 seconds at 10 kilometers?
It's Joe, it's about 1 degree C. I need to look at the lookup tables, but broadly speaking, 1 degree C at that level.
Thank you very much. Another question here from Vladimir. How to safety test a cable without the danger of damaging the cable?
Yes. So when you're doing the test, we use heat sources to generate the heat around it, and you need to be really careful. There's different partners have different methods for doing this. I think one of the example I showed there, they had a heat gun. So obviously with the heat gun, you have to be very, 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 very careful. But you can also control the levels of this. So it's depending on which. There's some actual specialized ones that don't go above 85 degrees C. Some guys use this, but it's just making sure that you're at a distance where you're not causing damage, and you're measuring it as well, so you can see what the temperature is going up, so you can control it, so you can make sure that you're not doing it. But obviously, if you're using a heat source that exceeds the rating of the cable, which is typically 85 degrees C, it needs to be done with care, and whoever's doing it should be trained beforehand to do that, so that they can do it in a manner that doesn't exceed the cable temperature rating.
Thank you, Richard. Question here from Eric. Are there training possibilities available, please?
Training possibilities?
Yes.
Yes. Yeah. We train all the people we work with, and that's either through our partner network or ourselves. The last 12 months has been particularly challenging in that front, but actually we found that we can do it remotely with a good internet connection, sort of the right people on both sides. It works quite well, and I think with this technology, the systems are pretty straightforward. They're very easy. With some customers, they buy a system and we don't hear from them. They read the manual and they work it out themselves. And others want a bit more, want formal training, and we build that into the package. But the other side is the fiber optics and putting the cables in. You splice it and dealing with fiber optics. There's an element of skill to that as well. But what's good about that is it's very similar to the skills you need as a telecom operator. So in most countries, there's telecom contractors that can do it, or people can receive training from telecom contractors or from ourselves. So there's a number of different options. But yes, absolutely, it's something we offer. But I just want to emphasize the system is pretty simple, so it's not extensive training required typically.
Thank you, Richard. Another question here from Mustafa. Hello, can you please inform sales channel contact for Turkey?
Yes, well, you have my contact details here after this, Mustafa. If you send me an email, I will certainly follow up with sales contact details for Turkey. And yeah, we've done a lot of work there, so I'd be very happy to talk.
Thank you. I've got a two-parter from Thomas. How do you calibrate the temperature measurement?
Yeah, so 99% of the time, it's literally plug and play, and it does it out of the box. You know, we supply the cable. The cable's designed to work with the system, so there's no real temperature calibration required. You know, we don't typically need it for standard linear heat detection algorithms. But in some areas, if we use specialist cables examples, you can do it. And so what you do is you need to take 2 points typically and do a point and slope. So you take temperature measurement at those certain points, and we have fittings you can put on the cable, so you can measure what that is and then take a reference on the system. And then once you have the 2 points, you can then apply the slope and offset coordinates to that. So it's relatively straightforward, but almost never required, and certainly for the standard applications, it's automatically calibrated.
Thank you, Richard. Second part from Thomas. What are the typical failure modes of the system?
Damage to the cable is the primary one. If somehow the cable gets cut, and if it's installed well, and you know the way other cables that happen, that doesn't happen very often. It's very robust. I think in some cases, in a control room environment, if it's operating outside the specifications of the controller, so you know we recommend a climate controlled environment. You know, it's certified up to 45 degrees C, 50 degrees C standard, but that's, you know, some cases it can go over that, and if the system goes over that temperature for extended periods of time, that can put stress on some of the controllers. But it's very unusual. It's almost always mechanical cut to the cable somewhere on the route. As we said, there's no corrosion, no moving parts, so there's no real. It's pretty passive. There's no way, unless someone actively interacts with that cable somehow, that it can fail typically.
Many thanks. I've got another question here from Tom. Congrats, great presentation. Do I understand it correctly that the full 10-kilometer 4-channel system is VDS certified as per EN 54-22? Do you also have the UL 521 and FM approval? Best regards, Tom.
Yeah, well, the approvals is an ongoing process. So yeah, we're going through those. So yes, we're doing the EM54 and the UL 5210, and we have some systems approved and some systems undergoing approval. So the 10-kilometer is under approval at the moment. We would hope to have that completed within the next 3 months, I would hope.
Thank you very much. A question here from Sergio. How many zones can I set for 2 or 4 kilometer units?
The same number, 1,000 zones, and it's a large number, and no one ever really gets there typically. So in theory, it probably could be increased on one, but because we haven't had the requirement, we have it at 1,000 at the moment. So if anyone else has any more than that, let us know, and we can look at whether that needs to be increased.
Thank you. Another one from Tom. PS. Do I understand right? You can measure 10 kilometers with a temperature of 1 Celsius within 5 seconds?
Yeah, that's correct. And there's I think there's accuracy and resolution with these systems. I think the resolution is better than that. So the changes are more in the half degree C range. So yes, it's correct.
Thank you very much. Another question here from Miko. How to test the system? Do you supply a special tool for testing the system?
We can make recommendations. It really varies in which part of the world we're working with and what who we're working with. So I would say that the vast majority of people we're working with are doing the installations themselves, and so they have that capability. Normally they have their own methods in doing that, but if it's someone starting out from scratch, yes, we have recommendations of tools we've used and we would use, but it's with the proviso, it's in the environments we understand, and different countries, different standards, different test environments like that. But we certainly work with and provide advice on that front.
Thank you very much. Another question here from Jose. Do you have installations of this technology in road tunnels? And if yes, what are the recommendations regarding the installation versus the dimension of the road tunnels?
Yes, we have many road tunnels. Regarding the dimensions, I think if you could send me an email, I'll follow up on that, because someone knows better than I in terms of what the number of cables and spacing requirements are for road tunnels. But I'd be very happy to follow up on an email on that point.
Thank you very much. Another question here from Durav. Is there a problem if you use armored OFC cable for measuring temperature along the electrical cable tray?
We would always seek advice on the specifics of that project and look at the risk assessments. It's done in some scenarios. In some scenarios, the customers prefer to use non-metal, and normally the customers have the opinion of that. But we can certainly highlight, where the risks are in that front, and it'd be a case-by-case scenario, I think, depending on what the electrical cables. Again, if you want to send the details, I can get back on that more as to whether his specific example would be metal or non-metal.
Thank you. Another question here from Wouter. Dear Richard, can the glass fibre also be integrated within the pipe duct structure to be more robust for damage? How would temperature distribution be assessed in the tunnel?
Yeah, I'd have to look at where the pipe duct is in relation. It will almost certainly have some sort of insulating factor. So we'd have to look at it and then possibly have to test it. It's funny, for the distributed acoustic as well, we get a lot of questions on in ducts as well, and what the effects are. And in both cases, there's some reduction in the measurement sensitivity, but in some cases it's perfectly workable. So I'd have to look at that. It's interesting in tunnels. The only examples I can think of where we've installed within duct was actually during the construction process, and to monitor the temperature in the construction, because they were freezing the rocks as they were constructing, so it didn't fall apart. And so I've not used it in a linear heat detection capacity in a duct. So yeah, again, send me the details and follow up on that.
Thank you much. Another question here from Andreas. What is the typical maintenance requirements of the system over its lifespan? Is there any intelligence the fiber optic transceiver proactively monitors itself and reports its own condition status besides the fiber cable breaks?
It's a very good question, and that's also a good point to make. That if you do have a fiber break it will inform you that have a fiber break, and it will continue measuring, automatically switch up to that break and continue on. So that, yeah, I mean, the system does have a number of self-diagnostic features. So, for example, with the relays, when I said there's 50 relays, 6 of those are set aside for fault diagnostics. So the first 6 give information on the system. So if it has a fault that comes under one of those 6 categories, it would send a situation to the fire alarm control panel. So yes, it does have that. If you have a fault, it will detect, and you will get a signal to the fire alarm control panel.
Thank you, Richard. Another question for you from Levent. Thank you very much for a good presentation. What is the IP rate of fiber sensor cable via fiber AT?
Oh gosh, off the top of my head, can I get back in that? I want to say it's 6.1.1, but it's on our data sheet. Again, if you send an email on that, I'd hate to say something that's wrong on this call, but yeah, again, I can send the data sheet with that on.
Okay, thank you. Another one here from Vivek. Is it compulsory to have 2 control panels at both ends of the tunnels?
No. So it's a very good question. So the example I gave there was an example of redundancy with the control tunnels at each end. And that was for a single tunnel. You could have the 2 controllers at the same end, but if you wanted to have the same level of coverage, you would need to have the cable looped, and you need to have the cable sort of come back on a different path. So if one element was cut, the other would be safe. So you can do it with you can put them on the same end, but you need to adjust the cable configuration accordingly. And it depends specifically in some cases. So I think I showed the example with 2 tunnels there. Some cases it happens naturally because you can do the cable out on one tunnel and coming back on the other tunnel. But where you've got a single tunnel, it would probably make sense to put them at the other end. But then, if you don't have a control on either end and you want to do it that way, then maybe you do the second cable back. So every scenario has its own thing. So the answer is no, you don't have to do that. You can put them on the same end. You just have to tweak the way you run the cables.
Thank you very much. Another question here from Carl. Are all 50 onboard relays fully isolated?
I believe so, but I will get back to Carl on that one.
Thank you, Richard. Okay, final question for you, and you've been absolutely superb. You've done 20 questions already. Another final one from Farouk Zaman. Thanks. You discussed in loop installation after I posted the question. My understanding is that this allows the light to come back to the controller from either side if there's a cut in the middle. Great presentation and awesome technology.
Yeah, thank you very much, Rick. Yes, yes, the loop configuration is exactly that. You get it from both sides, and if you have the cut, you're still measuring to either side. So similar to the question before that, with the loop configuration, you remove the need to have two controllers in different locations. So as we said, if the customer end user only wants cable cut redundancy, which as we said is the main threat to the sort of reliability of the system, you can then do it with a single controller with the loop cables, or 2 controllers in the same location if they want that. So yes.
Richard, I'm going to finish on another one. Actually, I've got one more here from Alan. When used for wide area fire detection, example in a single wide floor area monitoring, how does the system determine the location of the fire based in the distance reported or detected?
Yeah, no, it's a very good question, and it really depends on the cable configuration. And I haven't gone into, so we have other presentations and application notes on industrial facilities, which goes into that those questions much more specifically. And you know, it depends. And what we're seeing, for example, in warehouses now is that the cables not only run on the ceilings, but it's run on the shelving units as well. So you get really close to the fire, and that's sometimes when we get the more advanced visualization software, because you get the exact precise measurement within what meter. But to make sense out of that, sometimes that's where the visualization software comes. So you have a visualization, and then it shows you on the software precisely, which shelf, which location, which part of the warehouse. It shows that. So the greater the density of the cable, both at ceiling level and if it comes down from sea level, gives you more information and location at that point. And we're increasingly seeing that is becoming more and more popular.
Absolutely superb, Richard. I'm just gonna finish up the Q&A. Some people's been putting some notes. Great presentation, superb. Really enjoyed it. So thank you very much for a fantastic presentation and Q&A session. That was superb. You did over 22 questions there. Brilliant.
Excellent. Well, thank you very much. I mean, it's great questions, great participation, and thank you, Martin. Fantastic.
Yeah.
We have this opportunity, especially now, where it's yeah.
I've still got another 20 questions here, Richard. So as I said, you will get a copy of these questions, so you'll be able to see they are. And ladies and gentlemen, I know a few of you are asking in regards to the copy of the recording and the presentation. The live recording will be on demand within an hour after this live recording now. If you would like to drop Richard an email in regards to his PowerPoint presentation, I'm sure Richard will come straight back to you in regards to that. Is that okay, Richard?
Yeah, of course. Yes, please do.
Thank you very much. Ladies and gentlemen, I have to say a big thank you to Richard from Bandweaver Technologies this morning for an excellent presentation. And as I said, it's a superb Q&A session. Over 22 questions answered. Absolutely brilliant, Richard. Thank you very much.
Thank you.
The webinar today, as I said, will be on demand for you to rewatch as well. Once again, a big thank you to Richard from Bandweaver Technologies. Thank you to everybody for attending, and we do look forward to seeing you all at our next WeRail webinar. Thank you all, stay safe, and goodbye.
Bye. Thank you very much, everyone.